A small town in southern Arizona has a declining population that follows exponential law. The population decreased from 8,000 people in 2005 to 7,200 people in 2007. Predict the population in 2020. So since this problem says that the population is following exponential law, we know that this is an exponential decay situation. So for any exponential growth or decay scenario, we can always use our basic exponential model, which will be a is equal to a sub 0 e raised to the rt. And remember, the letter that we're choosing here, a, could be any letter. So, if you have a book that was using q, it could be q is equal to q sub 0 e raised to the rt. Okay, don't get stuck on that value. A, doesn't matter what letter is chosen here. So I always recommend that you organize the information in the problem in a table format. So the first values that we have are the values of 8,000 people in the year 2005. So rather than entering a time value here of 2005, I'm going to instead redefine my value, t, or my variable t, and instead I'm going to let t equal the number of years since the year 2005. So t is the number of years since 2005, because then that's going to allow me to use a time value of 0. And we know there were 8,000 people in that year. In 2005, there were 8,000. Then it says there were 7,200 people in the year 2007. So that's 2 years later, so that would be a time value of 2. And we're interested in the population in 2020, which would be 15 years later. So when t is equal to 15, we're looking for the amount. So remember that the a sub 0 in this model represents the initial population at time 0. So we have that information. That's a is equal to 8,000 e raised to the rt power. Then we move on in the table. At a time of 2, we have 7,200 people. So that's going to allow us to substitute into our equation. 7,200 is equal to 8,000 e raised to the r times 2. So when t equals 2, my amount is 7,200. And this is going to let us solve for r, which is the relative decay rate, or it's called sometimes the decay rate constant. So we need to divide both sides by 8,000 so that we can isolate the exponential quantity. I'll let you put in 7,200 divided by 8,000 in your calculator. You want to always leave this as an exact fraction or an exact decimal. And in this case, it does work out to an exact decimal of 0.9. And then I'm going to go ahead and reorder r times 2 here. I'm going to reorder that as 2r. And then we'll rewrite this in logarithmic form. Our base is going to be e, so that would be log base e of 0.9 is equal to 2 times r. But we realize that log base e is really the same as natural log, so to save myself some room here, I'm just going to replace that with the natural log of 0.9. Therefore, when we divide by 2, we see that r will equal the natural log of 0.9 divided by 2. That's the exact value for r, and then we can go to our calculator to get the estimate. I encourage you to do so that you can check your calculations. And we'll get r is about negative 0.05. And remember, we expect r to be negative because this was an exponential decay scenario. Now, negative 0.05 is a rounded decimal, so we do not want to use that in our future computations. So I recommend that you either use the store feature on your calculator and store that, or you continue to leave r in exact form, which would be the natural log of 0.9 divided by 2. All right, so now we can write our model. So the exponential model for this situation, remember the model is just the equation that relates the variables in a scenario, will be a is equal to 8,000 e raised to the negative 0.05 times t power. That's my model. And now we want to know how many people there will be when time is 15. So that's looking for a of 15. And again, that was definitely a calculator problem. Reminding you once more that we're not actually going to enter in the negative 0.05, but rather you're going to use your stored value, or you'll enter it as the natural log of 0.9 divided by 2. So pause the video and check your calculator. And I'm getting 3,630.02, and that would be the number of people that we would expect in this small town in the year 2020. And I know you can't have 0.02 of a person, or at least we can't measure that, but I do like you to go ahead and include your decimals so that we can check the accuracy of your computations. Now, there's another way to tackle this exponential decay problem, a way that does not use this general exponential model that we just used, but instead, the second method requires us to determine the multiplier. So instead, if you want to determine the multiplier, this will allow us to attack this problem in a slightly different way. So I'll show you that method as well so that you can pick what method you like best. Still looking at this from a table perspective, that at time 0 we had 8,000 people, and 2 years later there were 7,200 people in this little town. So if you want to determine the multiplier, remember exponential growth and decay is always characterized by repetitive multiplication. In other words, we should take 8,000 times some number, and it'll give us 7,200, and that's what we would repetitively multiply by to give us subsequent y values in this table. So written out mathematically, basically we're saying that 8,000 times some number x will give us 7,200. So to figure out x, we obviously have to divide both sides by 8,000. So 7,200 divided by 8,000 will give us 0.9. So my multiplier, what I'm multiplying by repetitively, is the number 0.9. So I could continue to multiply by 0.9. For example, if I multiplied 7,200 by 0.9, that would give me 6,480. So if I wanted another value in my table, this would be 6,480. But notice that my time increment here increased by 2. So if I increase by 2 again, then that would be at a time of 4. All right, so if we determine the multiplier, then we're going to use that multiplier as the base of our exponential function, because we would multiply repetitively by 0.9. So instead of using e as the base like we did previously, we're going to use 0.9 as our base. So we'd start off with our initial population still of 8,000 people, and now 0.9 is going to be the base, since I'm repetitively multiplying by 0.9. And what I recommend you doing is start with an exponent of t, time, and let's just see if this works. So what I mean by seeing if it works is, well, when I plug in 0, I better get 8,000. So let's test that. So 8,000 times 0.9 raised to the 0 power. We need that to equal 8,000. Well, 0.9 to the 0 is 1. 1 times 8,000 indeed does give you 8,000. So that checks out. All right, now look at your second ordered pair. 2 time of 2 should give us 7,200. So in other words, 8,000 times 0.9 raised to the second power, we need that to equal 7,200. But if you use your calculator and test that, you're not going to get 7,200. You're actually going to get 6,480, which was the value we needed next. And what this tells you is that you have to adjust your exponent. So in this case, because our time values, get rid of t up here, because our time values, we were going up by 2 each time, then my exponent here needs to be t divided by 2. Now think about why that works. Let's try that second data point of 2, 7,200. Try this out. 8,000 times 0.9. So now if I substitute in a time of 2, but I'm actually going to do 2 divided by 2, then that allows me to see that I'm going to have 0.9 to the first power, which indeed will give you the 7,200 that we wanted or that we needed. All right, so this would be our model. Rather than using our a sub 0 e raised to the rt, we can find our model using a base of 0.9. And it turns out that this model is equivalent to the previous model that we found, just written in a slightly different way. So now if we're interested in the number of people in 2020, then that's the number of people 15 years later, since T began in 2005. And indeed, if you use your calculator and you substitute 8,000 times 0.9 raised to the 15 divided by 2 power, you'll get the same exact value that we had before. 3,630.02 people will be the number of people that this population or this town will have in the year 2020.